I'm naturally not the best when it comes to coordination, and all growing up, I often found myself struggling with rhythm-based activities. With the designated task of designing a 20-hour skills program, I thought it would be a good opportunity to challenge this pre-existing disadvantage and commit myself to learning how to skip with a jump rope.
Learning how to skip starts with defining what a skip is, which is by definition jumping over a rope which is held at both ends by oneself, turned repeatedly over the head and under the feet. By utilizing this definition, it allows me to provide a clear insight into what a repetition looks like and enables consistency in counting the skip during my pre and post tests. This definition can also be applied within the transfer test when changing the rhythm or type of skipping. With that in mind, the end goal of the 20-hour skill practice, I have challenged myself to increase the amount of skips that can be done under a 30-second time frame after a 4-week period of skill acquisition training. The skill acquisition training is designed and led by the concept of a constraint-led approach, which by definition states a contemporary approach aimed at providing movement practitioners the ability to enable people to acquire coordination and movement control with time. It exists as a non-linear pedagogical approach that utilizes Newell's model of constraints where the environmental, organismic, and task constraint can be applied to assist in the acquisition of a new skill. The constraints at hand are Newell's model of constraint. Newell's model of constraint emphasizes on the interaction between the complex system and the organismic, task, and environmental constraint that is applied to a task. Organismic constraint is the physical structure of the individual. In a skipping context, it can be the height and coordination ability of the individual. The task constraint is the parameter or rule surrounding the task, such as the tempo, equipment, and required technique that is demanded. Environmental is the interaction between the individual and the external environment, such as the surface, weather, or altitude. All these constraints work with one another to enable perception-action coupling, where the informational exchange between the individual and the constraints would couple with the reaction in response. This leads to emergence of different traits of co-coordination that may become optimized with practice and experience.
To understand how I, as a learner, am going to adapt to acquiring a new skill or improving upon it, we must first understand the dynamical system theory that is in place during the skill acquisition.
The dynamical system theory states that a complex system exists as an interaction of a self-organizing, multi-component system that evolves over time. It is through the interaction of degrees of freedoms that are utilized to achieve a common task.
A real-life example of the application of a dynamical system theory can be a beehive. When we look at a beehive, we can look at multiple components interacting with one another to achieve a common goal.
When we look at a beehive, we're looking at the components or degrees of freedoms, which are the workers, the queen, and drones, all interacting with one another through actions of feeding, care for larvae, and collection of pollen to produce honey as a means of achieving a common goal.
As a complex system, I can be interacting with the jump rope and the constraints surrounding me. I can utilize these information and physical constraints to emerge a new coordination pattern to maximize efficiency in my goal or movement.
A complex system can be analyzed through three components that assist in how a system adapts to constraints of a new task. A main variable of a complex system is that it is non-linear, meaning that skill acquisition and optimal motorization is not a linear progress, but rather a slow and gradual shift. This application is applied through the power law of learning, which suggests that learning occurs most rapidly during the early stages of skill acquisition, with performance improvements gradually diminishing as the individual approaches his mastery. This learning process lies heavily in the usage of constraint manipulation rather than instruction-led practice. Self-organization exists as a means where the system creates its own internal structure and patterns from local interactions within the organization's environment. This process is completed with the absence of external factors or central commands. Take, for example, the diagram shown here. We can understand how movement and skill emerge from the interaction between the individual, task, and environment. As a result of this, we can see how self-organization can lead to shifts in attractor states, such as walking to running, where this shift is seen in the attractor landscape. The final component is Bernstein's degree of freedom, which can be defined as the coordination of multiple independent variables to produce a purposeful action. In the context of skill acquisition, the degrees of freedoms of a skill can be manipulated to produce a desired outcome. For instance, by simplifying the complexity of a movement, it can allow for the individual to adapt and better understand the demands of the movement. An example can be seen here where I reduce the speed of the swing in a jump rope movement to allow myself to have easier timing and coordination and allow myself a more natural flow of the movement as I progress. Freezing can also be implemented, restricting the movement of a skill by focusing on a singular component. Doing so would allow a systemic approach to breaking down the requirements of the movement and ease into a stable pattern. This can be purely focusing on the wrist movement of skipping to allow an understanding of the range and speed of the movement in that particular component. By simplifying the movement through the removal of the other moving components, I can focus on the timing and rhythm of the movement while reducing coordination demands. The opposite can be applied, where the variability of movement can be introduced by increasing the degree of freedom. This can be achieved by managing the physical or informational constraint of the task at hand, for instance, allowing a basketball player to dribble before shooting. With the context provided in regards to a constraint-led approach, modification and application of these constraints will impact the long-term changes to the organization of a complex system. In this context, me as the learner, creating lasting changes in the perceptual modal landscape as the individual searches for stable and functional states of coordinations, which are known as attractor states. In the skills program, I can see how different constraints affect the way I learn and perform. Things like the task itself of working towards my ability to be efficient in my coordination during the skipping motion, my physical abilities, the environment I'm training in, all influence how my skill develops and changes over time. It is simply my search, as a learner, to search stable and functional states of coordination that eventually leads to long-term changes to the organization of my movement and create certain efficiency that maximizes the capacity of my learning.
Okay. With the concepts discussed, I can utilize the information in regards to constraint-led approach to allow myself to acquire coordination and movement control with time.
By taking these into considerations, a 20-hour structured training can be implemented through a constraint-led approach. By utilizing the environmental, organismic, and task constraint of the task at hand, we can optimize our performance and increase our efficiency and coordination of the skipping movement. Therefore, 20 hours of structured skipping practice will lead to increased efficiency and coordination by movement, leading to increased number of skips in a 30-second time frame. A pretest was conducted where a time trial with 30 seconds was done where I performed as many skips as possible. Using the definition provided at the beginning of the presentation, I count the number of repetitions based on the rope crossing over my head and under my feet. This test was performed prior to the commencement of my 20-hour project, where as shown here, a lot of inconsistency and lack of efficiency in my movement can be seen. These are the rhythm, poor timing, and inconsistent height of my jump. The same test was performed at the end of the 4-week period, with the main goal of seeing if there were any differences in the quality of movement and efficiency of the system. This is measured via height of jump, tempo of skips, and number of repetitions achieved within the 30-second time frame. These concepts will be later discussed during the result and discussion section of this video. To add on, a transfer test was performed a week after the post-test. The conditions are changed where the rope length is reduced and now the time length of the task is unlimited. The goal is to see if the system is capable of adapting and utilizing self-organization to perform a similar task under different conditions. It is also important to note that all tests performed are done over 3 trials with scores averaged to provide better reliability. The program was broken down into a 4-week design with the goal of addressing each different component of the skill and utilizing change in constraints to achieve a certain outcome. These constraints that were influenced were manipulated to encourage a goal behavior or coordination pattern to emerge as a result. During the first week, the focus was on building a solid foundation by isolating and practicing the fundamental components of the skipping movement. By breaking down the skills into smaller parts, I was able to refine each action individually, enhancing both efficiency and familiarity with the overall technique. During this stage, self-discovery played an important role as I explored emerging movement patterns while developing the skill, such as finding a comfortable tempo, managing jump height and weight, and establishing a personal rhythm with the rope. To support this learning process, task constraints were deliberately manipulated to free certain degrees of freedom, allowing for a clearer and more detailed understanding of each movement. These principles are progressively applied in the following weeks, where the goal is to deepen the attractor wells and introduce greater variety into the movement patterns. By continually adjusting task constraints based on performance, week 2 and 3 focus on expanding the foundational skills established during the initial stage of training. Week 4 then serves as an opportunity to implement the skill in a more complex and integrated manner, as I have consolidated the movements developed in the earlier stages. Furthermore, at the end of each week, I will repeat the trial to evaluate how the system has evolved and adapted, allowing me to observe changes in coordination patterns and overall skill stability over time. As mentioned earlier, week 1 focused exclusively on developing the fundamental components of the skill, which were divided into 3 key elements: the jumping motion, the rope's rotation, and the rhythm that synchronizes both actions. During practice, I learned to optimize movement efficiency by applying less force through my feet and focusing on a light, continuous bounce rather than a full jump. This reflected a shift towards a more stable coordination pattern with reduced dorsiflexion and energy use. Anchoring my hands near my hips and relying on wrist flicks to rotate the rope further supported rhythm and control, showing how the motor system self-organizes into a more efficient movement pattern as skill develops. Having assembled a coordination pattern within week 1, I began to manipulate my constraints to shift focus on gaining control of coordinative structures. This meant that I was performing the task at varying tempo, rhythm, and environment. Doing so, the learning process is characterized by search and exploration, as I continually adapt my patterns to match my constraints provided. This enables self-correction and the search for key information. As such, metastability was bound to occur, in which a stable coordination pattern would appear that seeks to achieve a functional goal with more than one movement solution. This can be a shift of my jump height, wrist speed, and the ability to adapt to external stresses. The week after, the focus is still placed on ensuring that the learner is still deepening their attractor state. In this block, there's a shift towards more complex tasks that still encourages search and exploration within the learner. This came through in the manipulation of task constraint, ensuring that the learner is still trying new patterns that originate from the stable pattern developed during week 1 and 2. Reaching the final stage of Newell's model of learning, Block 4 focuses on optimization of control within the learning process. At this stage, the learner already demonstrates stable, efficient, and adaptable coordination patterns when skipping. The goal is now to focus on refinement, adaptability, and performance optimization under varying constraints that would occur in the transfer test. Overall, the training proved successful with a steady increase in the number of consecutive skips from 12 in the pre-test to 38 in the post-test. The most significant improvement occurred between week 2 and 3, where performance increased from 22 to 32 skips. This period aligns with Newell's second stage of learning, as I began to constrain my cognitive structures and refine movement efficiently through more stable and organized patterns. We also saw a reduction of the post-tester retention test, where it changed from 38 to 34 skips, showcasing a 10.5% decrease. The retention test to the transfer test saw a 14.7% reduction in skips, dropping from 34 to 29 skips. The byproduct of the 4-week training program led to an observable improvement, showcasing an increase in the number of repetitions the learner was able to perform through each weekly trial and in the post-test. Therefore, the application of a constraint-led approach led to an increased efficiency and coordination in my movement, leading to an increased number of skips in a 30-second time frame. These improvements were my jump height, speed of my swings, and reaction time to the rhythm of the rope. This result can be attributed to the process of self-discovery during my learning stages, as I optimized my movement solution to help me identify the transition in attractor states. With the application of constraints, the strength of the program stems from the diversity of constraints. By changing rhythm, skip patterns, environment, and rope length, the learner was subjected to a multitude of challenges that encourage self-discovery and to adapt to changing circumstances. Doing so enabled me to utilize a sense of metastability where the wrist speed and jump height was kept consistent as a result of week 1. Adding on, the encouragement of self-discovery allowed me to compensate and adjust my technique based on my organismic constraints. These were my height, arm length, and reaction time. However, the program still came with its own faults. For instance, the lack of controlled practice conditions. Although varying constraints promote adaptability, a lack of controlled practice environment led to difficulty in identifying whether performance changes came from skill improvement or adaptation to temporary conditions. Another issue regarding this is practicing with differing settings or with changing rope lengths may have introduced too many variables at once and overload the learner. Furthermore, limited task complexity progression where increased task demands lacked opportunities for more complex coordination challenges such as crossovers. As a result, the perceptual motor landscape may have not been fully explored or tested for adaptability to more advanced forms of skipping. To address this in the future, I will provide a greater variety of skipping rhythms to deepen my perceptual motor landscape, ensure that I perform in the same environment throughout training. This project demonstrates how the constraint-led approach can be used to improve coordination and movement efficiency across various skill-based activities. By manipulating task, environmental, and organismic constraints, practitioners can create learning environments that promote self-organization and adaptability rather than relying solely on instruction. Beyond skipping, these principles can be applied in sports coaching, physical education, and rehabilitation to support learners in developing individualized and efficient movement solutions. This learner-centered framework encourages exploration, confidence, and long-term skill retention.